Hello, everybody. Welcome to another discussion in dynamics. Plan for today is following. I would like to start with a brief lecture overview. I usually do it. I don't do much lecture reviews. Today I decided to do it. And then two examples. I am pretty sure that we are going to finish everything on time. I'm 100% sure that we are going to do everything that Professor Sonny asked us to do today. And info session very quickly. So I hope you got my email. Yeah. So basically, I'm recording those discussions. I'm posting videos on YouTube, and you can access the channel via link you got you have in your email. You should receive on Sunday. There's a link on Canvas, or you can search for the channel Dynamics for Non-Dynamicists. This is the name of the channel. I can maybe explain you why I choose that name, because it's not that the viewers are non-dynamicists, yes? The reason for that name is that I try to speak about dynamics using very, very simple words, very short sentences, and I would like to have a clear message, yes? That's why I just choose that name, yes? I hope I am successful in that, because it's my goal. Yeah, you will tell me later this semester, okay? Okay, quick reminders. Sorry for repeating myself for the third time. Probably this is the last time I'm going to remind it. So first of all, please familiarize yourself with the problem statements before coming to our discussions. You know that it's beneficial for both sides, yeah. And again, practice makes progress. If you agree, then try to tackle the homework with this thing, okay? Don't use social manuals. I think it's a great way to learn, yes? And I don't know, if you want to make progress, if you want to learn, tackle homework problems by your own. It will, I guarantee that you will be successful. Yeah, I guarantee you the success at the end of the semester, maybe even beyond that semester, yes? I guarantee you, I promise you, yeah? But choice is yours. You're adults, I treat you like adults, choice is yours, okay? Yeah. I don't know. Oh, and of course, if you run into issues with your homework problems, you know what to do. Yeah, we have Piazza, or just stop by our office hours. We are here to help. Okay, guys. I don't know, enough of motivational speak. Yeah, I feel like a life coach. So let's do brief lecture review, or any questions. Yeah, let's do that review. Okay. Yeah. As you can see, I prepared quite a lot before our discussion. But don't worry, you can take a picture right now, or you can maybe visit our YouTube channel, yeah, and you can just put down your notes, yeah, write it down, yeah. So what I would like to do today is basically I'm going to repeat what Professor Sonny was talking about yesterday. Okay. Today, however, I would like, and what I mean by that, I would like to compare Cartesian coordinate system to polar coordinate system, yes? And so now let's focus on the left-hand side, okay? So what do we have in here? Story goes like that. We have a particle, okay? Actually, before we have a particle, we have a trajectory, okay? This trajectory. And our particle follows that trajectory, okay? At time instant, I don't know, 2 seconds, it is in here, okay? T equals to 2 seconds, okay? But let's say, I don't know, 3 seconds after, at time instant 5 seconds, it will be here, okay? Time instant 5 seconds, yeah? That means that our position vector R that follows our particle, R is a position vector, yeah? It basically, so it will be R of 5, yes? R of 5. So it changes, vector R changes in time, yes? Because at time instant, I don't know, 9 seconds, our particle will be here. Will be here, okay? So now our R vector is going to change not only the length, but also the incline, yeah? In other words, vector R changes in time, yeah? You all got it, yeah? And there are different ways to describe that motion, yes? One of the ways is to express that motion in Cartesian coordinate system, What is characteristic about Cartesian coordinate system, you may ask? Those two guys, those two little guys, I and J. These are our unit vectors. Yep. And what is more characteristic about them is that they are constant. I always points that way. I always points this way, regardless of anything. And J always points upwards. Okay? What do I mean? Yeah, you all know about it. We all know about it, yeah? Moreover, if I take a first-time derivative of a constant vector, d dt of I, this will be basically zero vector, yeah? This will be 0, 0, 0. Yeah, because it's constant, yes? I can say the same about J. Okay, and that's why it's so easy to write it down, yes? To write down expressions for example, position. Here and here. This is position, yes? Velocity is first-time derivative of position, yes? That's why our vector would be x dot, y dot, z dot. By the way, position was x, y, and z, yeah? And again, if we would like to go to acceleration level, we have to differentiate velocity vector, and we will obtain x double dot, y double dot, z double dot, yes? That's actually all I would like to say about Cartesian coordinate system. I and J are constant. That's all. Any questions? Okay. So now polar coordinate system, okay? And the story goes like that. In here, we have exactly the same motion. Exactly the same motion. So that means that we have exactly the same trajectory. This trajectory is exactly the same. As previously, yeah? And that point, P, does exactly the same motion. The motion of that particle P is exactly the same as the previous one. And we have exactly the same vector R, exactly the same position, okay? The only thing that changes are our unit vectors. This time, they are not constant. This time, our unit vectors will change in time, okay? That's the only difference, yeah? So let's do maybe exactly the same what we did like 5 minutes ago. This is time instant 2 seconds, I said, yeah? So now at time instant 5 seconds, our particle will be here, okay? This is time instant 5 seconds. And that was time instant 2. So we can see that our R will be here. Oops. And that will enforce our UR to change, orientation, to change incline. UR is always aligned with R, okay? UR will follow R. One more example, at time instant 9, I believe that we were here. Yeah. So at time instant 9 seconds, R will look like that. And once again, you can see that our UR will change direction. Yeah. UR always follows R. That's why it is not constant. Yeah. I think it's clear. Yeah. So now let's see how this impacts our equations, okay? But before doing that, I would like to say that the incline of UR is defined by this angle, theta. Theta also changes in time, yes? Sometimes it can be smaller, sometimes it can be 90 degrees, sometimes it can be 0 degrees. Yeah, it also follows vector R. Okay, so now let's see how this impacts our equations. So I think I will need some help. And by the way, are there any questions?
I have a quick question. U theta, is it pointing in the C direction?
What is C direction?
So basically, it's perpendicular to
Yeah.
Y and X.
That's a good question. Y and X. no, u theta is always perpendicular. This is actually, I forgot about it. Thank you so much. Yeah, u theta is always perpendicular to ur, and it is always on the left hand side of ur. U theta cannot be here, never ever. U theta cannot be here.
Wait, so is u theta in the y-x plane then?
Yes, okay. Y-x plane. Yes. Okay. Yeah, this semester we talk about planar motion. Yeah, maybe with one exception, but mostly it's planar motion. Yeah? So u theta cannot be pointing the other way. Yeah. On Friday, we will see what will happen on Friday. Okay. Yeah. Okay. So guys, can anybody help me how to express r in this coordinate system? Anybody? What should I put here and what should I put here? And 0, not theta, 0. Yes, because, so if it's 0, I'm going to erase it, okay? Everything times 0 is 0. Because our UR and R are aligned. Yeah, R is aligned with UR. Yeah, that's why our R has only one component. The other one is always 0. IJ?
Are they not always, like, is UR ever pointing in a different direction than the R vector?
It is always aligned.
Oh.
Yeah. You can remember the previous drawing, yeah?
Yeah.
So if point P suddenly is here, R is going to always follow our point P. UR is like always going to change. UR will be pointing here. They're always aligned. UR follows R, in other words. Yeah. Did I shed some light on the thing? Yeah. Yeah. Okay. So that's it. That's all I want to say about position. And now velocity, okay? So since we have position, we can find velocity because we can always, the definition does not change. Doesn't matter what they tell you guys. So velocity is the first time derivative of position, okay? So let me plug this one in here. d dt r. So this is a product rule. Yes, this is product rule. So I can write d dt of r ur plus plus r d dt of ur. Okay, so this guy is basically r dot, and this guy, believe me or not, this will be theta dot u theta. Yeah, I believe that Professor Sunny explained that during the lecture yesterday. If you would like to have somebody repeating that, office hours, okay, or piazza, okay. I don't have time to do it right now. So this is our velocity vector. Velocity vector is r dot ur plus r theta dot u theta. Any questions? Suddenly, we have two components, yes? Even though our position had only one component, yeah, now we have two components of velocity. And this is everything because UR is not constant. UR is not constant. This is why we have two components. Questions? So acceleration, okay? Acceleration has the same definition. Definition is always the same. Doesn't matter what they tell you. d dt of velocity, okay? So that would be basically d dt of this long expression. And I'm not going to do the differentiation, okay? You can check out your lecture notes or visit us during our office hours, okay? Or piazza. So if you do this differentiation, guys, I'm gonna put here like 3 dots. You will end up with such expression. if I remember correctly, r double dot minus r theta dot square ur plus 2r dot theta dot plus r theta double dot. Yeah. If you write it like a couple of times, you can remember it clearly. Okay, so yeah, so we have basically exactly the same motion, just different way. So my goal is to show you that this is exactly the same motion, just the way we describe it is different. Yeah, and and these are the expressions for position, velocity, and acceleration. Any questions? Did I forget about anything? Yeah. So that's all I prepared for today when it comes to lecture overview. However, during class, the previous discussion, there was like one gentleman approached me after the discussion, and he asked me a question. So I decided to extend it a little bit. Okay. So how about we write down those three vectors, those three new vectors, in this way, in vector form? Okay. In vector form. So R will be basically R 0 0. Yes. However, let's keep in mind that this is expressed in UR, U theta, and K. Okay? Velocity can be expressed as R dot, R theta dot, 0. Again, UR, U theta, K. Okay? And acceleration, you all know what I'm going to write in here. R double dot minus R dot squared, 2R dot plus R dot double dot 0 in UR. Maybe just to save something, I can, instead of UR, U theta, UK, I can write R theta K. That's faster. Yeah, but I mean the same. It's the same. Okay, and he also asked me what would be magnitude of V. It's easy. Magnitude of V, or basically V, would be R dot squared plus R squared. Oh, sorry, square root. Yeah. What would be magnitude of A? Just take squares of components and take a square root of them. Sum them up and take a square root of them. A will be equal to R double dot minus yeah. Any questions? Okay. If you are shy, I will probably be here after the discussion for like 2 more minutes or 3 more minutes. You can approach me, or piazza, or office hours. Okay, guys, that's a brief lecture overview. I hope I didn't confuse you more than you were before. Yeah, I hope I shed some light on the thing. Yeah. Yes. Good. Yeah. Okay. Example number 1 then. So that's the theory. That's what it is. Now let's see how we use it. Okay. Let's do it. I don't hear any objections, so we can do it. Please familiarize yourself with the problem statement before we start our solution. Okay, so this is what we have. Okay, so maybe you guys can tell me what that color actually is doing. So basically, what do we have in here? We have a color that is on the road, yeah. So that road, if you look at this equation of motion, this one and this one, This rod is going this way or this way? Which way it is rotating? Exactly, yes. It's going this way. Yep, it's going this way. Omega increases, yes, this way. And that color is going farther from point Q or closer to point Q? Closer to point Q, exactly. So what would be the motion? The motion would be a spiral, yes? Like a spiral towards the center. Do you see it? Yeah, it's like a little spiral. That color would do that. However, yeah, so we basically solved the problem, yes? We know what the motion would be. This is the motion that will be realized. However, they told us what happens only at one time instant. Yeah, we solved it for every time instant. Yeah, they told us to tell them what happens to only one time instant at one particular time. Let's do it. So this is how I solve those problems. Yeah. So basically, I just write those two magical equations we found on the previous board. Yeah. So I just write this guy first. And then this guy. And I will just fill them out. I call it like that. Yeah. Okay, so basically what I mean by filling them out, I mean let's basically find what is r dot, what is r double dot, and so on, what is theta dot, and what is theta double dot. Okay, and so on. And then we will just plug all of these guys in here. And we will call it a day. Before doing that though, let's maybe find time t star at which angle theta reaches 30 degrees, okay? Time t star at which theta is equal to 30 degrees. Okay, so I believe I can take this expression. Theta is equal to 0.15 t squared, and 30 degrees is pi over 6, yeah? So our t will be equal to pi over 6 divided by 0.15 square root. Grab your calculators and obtain that this is equal to 1.8683 seconds. Okay. Now let's find velocity. Okay, so let me take this expression. I can copy it. And what do we need? We need expression for wait a second. So we need expression for r dot, yes? So we know that r is equal to 0.9 minus 0.12 t squared, yeah? So r dot, I'm not even going to ask you, okay? You all know that. This will be equal to 0.24 t. Okay, and also we need an expression for theta dot. So I think that theta was equal to 0.15 t star, and theta dot is 0.3 t. Okay? So this is like our general expressions, but now we are interested only in them at time equals to t star, yeah, which is equal to 1.8683. So if you grab your calculators, you will obtain that r is equal to approximately 0.4811, r dot is equal to approximately minus 0.4484. Theta is obviously pi over 6, which is 0.5236 radians. theta dot approximately 0.5605 radians per second. Yeah. Sorry guys, a lot of calculation, a lot of calculator stuff. Yeah. Okay, let's plug those values here, and we can obtain that V at that time instant is equal to minus 0.4484 UR plus 0.2697 U theta. And of course, this is approximately. Okay? Or maybe if you prefer this form, vector form, V will be equal to minus 0.4484, 0.26970, expressed in UR, U theta, K. Okay, 50% of the problem done. Any questions? Easy or easy? Any questions, guys? Yes. If they ask you for the velocity, they refer to the vector velocity vector. Yes. Nice. Okay. I will be during the exam when we write the exam. I will make sure that we write everywhere velocity vector, not velocity. Okay. Thank you. Any other question? So acceleration, yes, and I'm gonna do exactly the same, guys. I'm just gonna copy this expression or write it down. I'm just going to fill it out, and this is the end of the problem. Okay, so what do we need here? Aha, we need R, we have R, we need theta dot, we have it, we have R dot. Aha, so we just need to find R double dot and theta double dot. And they are exactly equal to minus 0.24 and 0.3, and they are constant, so I can also write them in here. R double dot is equal to minus 0.24, and theta dot double dot is equal to 0.3. Okay, so these are our values at time equal to t star, and plug-in values. So now again, plug-in values, grab calculator, and obtain that A is equal to minus 0.3911 UR plus minus 0.3583 U theta, or if you prefer this form, in R theta K. Okay, 100% of the problem done. IJ?
So when you're with the velocity and acceleration, you only have to find the scalar components. You don't have to find the actual unit vectors. Like,
No.
okay.
No, they are hidden here. Unit vectors are hidden. I will show you. I will actually draw those vectors, because we did 100%, we're gonna do more even. Okay, we're gonna draw those vectors. And I hope that that will answer your question, okay? Let's talk in a second. There was a question there, I believe. Lady in the Red. No, Lady in Red. I like that song. Okay. Yeah. No? Okay, sorry. Any other question? So think about questions. Let's draw them also, okay? Let's draw those guys, okay? If you have more questions, guys, let me know. So I'm just gonna, so they ask us to draw it in a configuration 30 degrees, yes? So let's draw it quickly. So I believe that this will be like that. 30. So this is the rod, and this is our collar, okay? And IJ, look, we know that those guys are hidden here. UR is in here. U theta is in here. They are just aligned with the rod. Or I mean, UR is aligned with the rod, yeah? And this angle this angle is theta 30 degrees. Okay, sorry guys, I can copy paste, yeah? You must redraw. For those of you who use pen and paper, which I actually really like, you must redraw it, sorry. Yeah, okay, so velocity was here, yeah? This is our velocity. So I believe that R component is negative, yes? And so it will be aligned with UR. So this will be 0.4484. Yeah, and theta component is positive, so it will be pointing this way, and it's like twice smaller than the R component. Yes, so that would be 0.2697. Okay, so this is our velocity vector at this time instant only. This is v. How about acceleration? So acceleration is here. So it has negative component in the r direction. So that would be 0.3911, and also negative in the theta direction. And they are of more or less the same length, yeah? 0.3583. Okay, so this is our acceleration vector at this time instant. This is A. And that's it. This is more than 100% done. Any questions?
So in the expression for theta, where it's 0.5 t squared, does it say that that's in radians, or do we just?
Always use radians, yeah, unless otherwise specified. But to be on the safe side, use radians. Okay, that would be my answer. Yes, you are correct. Yes.